Okay, AP class, it is story time. So let's make up a story here. Let's imagine that there is somebody ice skating. Nope, they're skateboarding. They're skateboarding down the street at a constant velocity. So we'll just say at some constant velocity. And then they hit a rough patch. So this rough patch right here is going to cause them to stop eventually. And they're smaller because they're stopped and they're feeling very sad. Okay, so V equals 0 meters per second. Now, the question is going to be how long, or what is the distance that it takes for them to stop? So let's put in some ideas here. Let's say that the coefficient of kinetic friction between this rough surface and the skateboard, let's call it 0.25. This is making a nice round number. Let's, not that it's needed, but let's just give this person, the skateboard system, a mass of 30 kilograms. And let's give their initial velocity as 10 meters per second. And I think that would be pretty much all we would need to know. Okay. So the idea here is how long does it take for them to stop? Now, as I mentioned before in a previous video, there are two ways you could go about doing this. One is you could figure out the forces in order to get the acceleration during this sort of rough patch. And once you have the acceleration, you could go into motion equations, so, motion, and solve it this way, which is really sort of a three-step way of doing it here. It's not going to be the best way to do it. In fact, let's reimagine this problem as an energy problem. So the way we do this is always, when you're always doing energy problems, ask yourself, what kind of energy do you have at the beginning? What kind of energy do you have at the end? And do you lose or gain any along the way? So in this case, we're going to start with the kinetic energy. We are going to lose energy due to the work done by friction. So we're going to be minus the work done by friction. And at the very end, you have nothing. You have nothing, right? Just like the lonely kid who has no friends. He has nothing left and no one. But he's all there by himself, sad and motionless. So there's nothing left over, right? It's not like he went up a hill, so he had potential. He's just literally motionless on a flat surface. Okay. So now let's put in some formulas here. It's going to be 1/2 mv squared. Okay, now the work done by friction. From your notes, work is always Fd. The force doing the work, in this case, is the force of friction times d equals 0. All right, now we're kind of getting somewhere. And again, I'm subtracting off the work done by friction because friction takes away energy. It never adds energy. That's why we're subtracting it. So this means that 1/2 mv squared minus, now the force of friction is always mu times the normal force. And you can see I'm doing this really kind of like every little step I'm showing. Now the normal force, let's do this a little bit bigger here. Now we have forces here. We have the force mg down and the normal force going up. Since we know that the skateboarder is not accelerating in the y direction, we know that the normal force has to be equal to mg in this case. Because again, in the y direction, the skateboarder is not accelerating. So the normal force is going to be equal to mg. So if I take this another step, oopsies, not equals. Mu sub k mgd equals 0. And now, remember, the point is we're trying to solve for d. How long does it take in terms of distance for this person to stop? Well, the first thing we can do is start solving algebraically. I'm just going to do this because I'm feeling kind of algebraic today. I'm just going to do this whole thing in algebraically first. I'm going to bring this whole term all over here. So it looks like that. Cancel, and then I'm going to solve for d. So v squared all over 2 mu sub k g equals d. And now this means that it's going to be 10 squared all over 2 times 0.25 times 9.8 equals d. All right, calculator time. So 100 divided by 0.5 times 9.8, 20.41. So this person will stop a little after 20 meters after hitting the rough part of the road or the rough part of the sidewalk. Again, we are able to do this simply by identifying, I'm going to go back to here, what energy do we have at the beginning? Kinetic. What do we have at the end? Nothing. And did we gain or lose any along the way? Yeah, we lost because of friction. And this is something I really want to stress for physics. Physics is always, the physics part of the problems are always super simple and super obvious. Like, good physics should be obvious and it should be simple. You have some kinetic, you lose it due to the work done by friction, leaving you motionless and with no energy. Now, the math part sometimes can get ugly. In this case, I don't think it was too ugly. You know, the mathematical consequence sometimes can be ugly, and that can be the hard part to solve. But physics should be always straightforward and simple and kind of obvious once you see it. So this is how we would solve a work energy problem or a conservation of energy problem with work included.